This is Introduction to Functional Programming. I'm Jack. So this was me in the summer when I had a little bit more sun on my face, but the northern weather has soon put pay to that. So I'm currently an acting software engineering team lead, previously a senior software engineer. I have created a few front-end applications, but back-end development is where I get my most joy. And I've been practicing functional programming for about 3 years or so now. So the target audience are anyone with little or no functional programming experience. Obviously, I'll explain what functional programming is, show the advantages of FP, and also highlight how we can improve code bases written in most languages. I will be doing my examples in Scala, but I will endeavor to explain the concepts without you really knowing the language. So there is some controversy over the definition. So I'll give you what I consider to be functional programming, and then I'll briefly address the controversies later on. So first of all, let's distinguish the difference between functional programming and a functional programming language. So the functional programming language might be something like Scala or Clojure or Haskell, whereas functional programming is a paradigm by which we can write code by. So let's look at what makes a functional programming language. So one element is first-class functions. So first-class functions are the ability to assign a function to a variable. So in this example, we've got our wake up person fn, and we're assigning that function definition to a variable. So in Scala, the arrow notation there you can see is how we're defining the function type. So the type on the left-hand side of the arrow is our input type, a string, and the type on the right is our return type, another string. So this is a very simple, crude example whereby we're passing in a single string input and it's passing that into another string using Scala's string interpolation, and then it's returning that back from the function. So now we can treat this like we would an integer or a class instance and pass it around our code base, and we can execute it at any point in time later on. All it needs is that single string input. So another aspect of the language is the ability to create higher order functions. So the ability for one function to accept another function as a parameter or have a function as its return type, that's what we define as a higher order function. So again, we've got our wake up person fn here, but this time we are passing it into another function called wake up. And because wake up is able to accept the function as a parameter, then this is our higher order function in this example. Wake up is our higher order function. And then you can see we're executing that function within wake up by passing it that single input that I talked about before. And that's it really. So most languages should be able to support these two features. And there are some parts of the community that don't consider them functional languages, even if they can support these features. But again, I'll cover that later on. But first of all, let's see what makes up functional programming, the concepts of it. So immutability is the first step. So we define immutability as once a data structure has been created, then you cannot change its state. So this example is the complete opposite of that. We are creating our address up here, and we're using the var keyword. So in Scala, the var keyword is how we define a variable that then we can change the value of it later on. So if you're coming from a Java world, for example, this is just creating a variable like you would in Java. But as you can see, we're passing it into a function, and then we're actually changing the value of that address variable. So then it's changed sort of either side of the function call. So this is quite simple to see where that value is changed, but you can imagine in a more complex example whereby address is being passed through various different functions, it's going to be a lot harder to see where our state has changed. So what we want to do instead, we want to manipulate the state of it and then transfer that new state to a new variable. So here we're using val instead of var. So in Scala, this is how we define an immutable variable. So if we try and change address further down the line, it will give us a compilation error. So from a Java perspective, you can think of this as defining a constant. So we're doing a very similar, well, logically we're doing the same thing here, but instead what we're doing, we're transferring that new value to a new variable so that address will stay the same. So we know if we use val in our address example here, then we know that address will stay the same, the value of that will stay the same throughout our code base. So in summary, when coding in Scala, don't use var. So pure functions are the other characteristic of functional programming. So the output of a pure function only depends on its input parameters and it carries no side effects during processing. So we go through the first part of that stipulation. So we have an example here that will return true if the minute of the hour is divisible by 6. I really like my tea. But we might get a possible different result every time we hit this function. We know that as everyone knows, time is constantly moving on, and that is our only internal dependency here, and we can't access it from outside the function. So we need to alter this if we want to make it a pure function. So this time, all we're doing, we're defining the time outside of a function and then passing that directly in. And we know now that the logic of the function solely relies on its input parameter. So the second part of the definition of a pure function is that it has no side effects. So the function shouldn't update any state, it shouldn't throw exceptions, it shouldn't perform any I/O, like in this example where it's calling off to a database. So again, this isn't a pure function. So pure function is quite a loaded term. It sort of implies that if you haven't got a pure function, then it's impure and bad and evil. I quite like the term transparent function. I think that's a little bit less loaded, but the industry does use the term pure function. So I'm just going to keep referring to them as pure because I didn't want to confuse matters. So if we follow these two rules when creating our functions, we know that they're also idempotent. So we know that every time we give our function the same input, we're always going to get the same output back. So no matter what functional programming definition you abide by, these pure functions can be written in any language. And that's a high-level summary of functional programming. And if you don't take anything else useful away from today, this slide is a really good place to start. So maybe some of you thinking, Jack, what magical world do you live in whereby you're creating applications and you can't write to a database or you can't store a state anywhere? So let's address that before you start thinking I'm losing my mind. So how do we actually do I/O then? So it's not magic, unfortunately. Hope that's not disappointed you all, like when you watched the last episode of Lost and you realize you've wasted 5 years of your life. I actually did this talk a couple of weeks ago for BBC Develop, and I made that joke without realizing the host who had introduced me 10 minutes earlier was wearing a Lost merchandise cap. Thankfully, he realized it was an unfortunate coincidence. Anyway, so we realized that I/O is necessary in an application, but by the definition that I've given you of a pure function, no application is 100% pure. We know that we have to do these I/Os as part of our application. But what we do is we rather keep our pure functions in what we call our functional core, and then we push out all the code that's doing the I/O, like HTTP calls and database calls. We push those out to the boundaries edge of the code base. So storing state, again, we know it's acceptable. It's just mutating state we don't want. So here we've got an example. We've got a car and we want to pass its MOT and we want to assign a value based on a hash map based on its model. So as you can see, I'm using the dreaded var keyword here again. So what this is doing in Scala, it's generating us some setters for this class. So we're calling off to these setters here to actually changing the values of those instance of the car instance. And what I'm also doing here is I'm returning a unit type as our function. So this is like Java's void return type. So it's not actually returning anything back from our function. So this is a very unfunctional programming way of approaching this problem. So this is our functional equivalent. So what I've done is I've separated out the processing with the actual data. So you can see we have our car class here, and then I'm actually pushing out all the operational logic into a separate object. So an object is just a Scala singleton class. What you might have also noticed as well, I've also turned the functions into first class functions. So they're actually being passed around rather than being sort of executed directly, as we saw before. And instead of changing the values of the actual car instance, I'm creating new instances of those car instances. So I'm using the Scala copy method here. And what copy allows you to do, it basically creates you a new instance of the class you're working with, but allows you to change some of the member variables inside the copy function. So in order to remove the immutability, I didn't need to turn them into first class functions. But now that they are first class functions, and I'm also dealing with the same type, i.e. a car, I can combine these functions together to create a pipeline. So here I'm creating a pipeline using the and then keyword, which basically says that I'm starting with the pass MOT and then combining that with a signed value using that and then. And then what that allows us to do is it allows us to pass in an instance of car, put it through our pipeline, and then we get a new car instance where the values have been manipulated. So in functional programming, this process is called functional composition, whereby we're combining these functions together. And that combined with the types is how we can allow data to pass through our systems within the functional world. And just finally on this, you can see we are using classes. You know, we still use classes, but the difference is we're not changing that initial data structure within those classes. So another way we keep state over a long process is recursion. So a recursive function is a function that calls itself during execution. So here we're trying to find the factorial of a number. We're passing in 5, and then it's just going to call a decrement of itself until it gets to 0. And then it's going to pass back that accumulation to the top of the function. So we're passing state through. We're passing state through as we're calling through the stack, but the key is that we're not mutating the state at any point. So that's a bit about the how. So why do we bother going through all this effort? So testability obviously is a big thing in our day-to-day tasks. Transparency, you know, if you can look at a function and know exactly what it's doing, then that makes it a lot easier to test. And also, as you'll see on the next slide, if you can pass the data straight into the function, then it makes it a lot easier to set up the test data. So here we've got a class to predict the outcome of a Bolton Wanderers football game. So I created these slides back in December when Bolton were losing a lot of games, but recently they've started winning a lot more. They won last night again. So I'm not going to change these slides because I don't want to jinx it. So we have our next result that we're trying to test here, but as you can see, it doesn't take any parameters. So what we're having to do is we're having to record the results beforehand just to test our next result function. So it'd be a lot easier and a lot simpler to test if we could pass in the recent results directly into next result. Similar if we're using a database to store the data. So we're having to mock out the database, and we're also contaminating our business logic with our IO. So alternative, we could retrieve the data from the database and then pass that directly into the function that we care about, and then it becomes pure again. And then we're testing the client separate to our prediction logic. So multi-threading. So one thing that can make multi-threading difficult is the mutation of global state, but we know that that isn't a problem with functional programming. So with Moore's law starting to catch up with us, you know, that increased rate of process power is going to start to slow down over the years. So we need to get more out of our code. Big data as well, you know, that involves distributed processing. So multi-threading is going to be very, very important over the next coming years if it isn't already. So say you've got a scenario where you're asked to look at some legacy code that's performing very, very slowly and you need to improve it. So you know that it's written in a non-functional approach. So you come across this snippet and you think, well, maybe we could put the first and the second process onto separate threads. But what we don't really know is from the really long process, whether it's got any hidden side effects in that the second process relies on. Maybe there's a change of state within that function. And also the variable A here is shared between the two functions. But if we come at it from a functional point of view, then we can run them on separate threads, those first and second line, because we know there are no hidden side effects. We know that there are no state changes, and variable A is immutable. So we know the value of A is going to be the same going into the first call as it is the second call. So a bit about referential transparency. So a functional is referentially transparent if it can be replaced with its value without changing the behavior of a program. So I'll show you an example of that and why it's important. So same scenario, you come across a different piece of code. So you can see here, there's a lot of repeated code that we can tidy up and can be removed. But again, we're going to have to check if the processor stores any state. So the mutation of shared state, so for example, here, if this processor shared some state that was being manipulated, the mutation of that shared state introduces the concept of time into a function call. So if state changes happen within a set of functions, then it matters when the functions were called and in what order. But we shouldn't really need to worry about this. You know, as a developer, you shouldn't need to care when a function was last called or when it be called in the future. And as we can see in this example, like times pass between the first long exec call and the second long exec call. Also, what happens to their exceptions? You know, if they're thrown and that causes a change in behavior of the program. For all these reasons, we can't treat them as referentially transparent, these calls. There's also no guarantee that they're idempotent. If we call long exec 3 times, we might get a different result. But again, if we come at it from a functional programming point of view, we know that they're idempotent. Therefore, we can treat them as referentially transparent, and we can swap out the duplicate calls with their values like so. So you see, it's a lot easier to refactor when dealing with pure functions. And as an aside, and when we're dealing with referentially transparent functions, we can cache the results. We know that if we're getting an input for a certain function call, then we can cache that result. And as soon as we see that input again on the same function call, we can go into our cache rather than processing again. So for all the previous reasons I've mentioned so far, I feel this makes the code more readable. You know, state and therefore time isn't a factor when debugging issues. And going back to my alternate name for them, a pure function isn't trying to hide anything from you. You know, it's transparent. What you see is what you get. So now a little bit about how the language, the functional programming language, helps us code in an FP style. So again, I'll be giving examples in Scala. These will be Scala features, but other languages will have a similar flavor of features. So this is just to emphasize how useful higher order and first class functions are. So say we want a function that iterates through a list of integers and gives us back only the even ones. So this might be a non-functional approach that we might take, but all we really care about is our modulus of 2 equals 0. The rest is very boilerplatey. We're having to create this imperative style loop. What we want to do in an ideal world is to take that important bit, the thing we care about, and pass it to our language framework and let that do the hard work for us. So in functional programming, the languages do have these built-in functions, and one of them is filter. So here we have a simple function is even, takes in an integer and returns a Boolean depending on whether it's even or not. We also have a list, and list has filter as one of its built-in functions. So what we're doing here is we're passing is even into filter, and filter is going to go through every element in the list, and it's going to apply the is even function to it. And if the Boolean ends up being true, it'll then pass that into a new list that it returns back. And if it's false, it'll just throw away the item. So in this example, filter is our higher order function and is even is our first class function. So it's simpler than the boilerplate example, I hope you agree, that we saw on the previous slide. And it gives a hint of the declarative nature of functional programming as opposed to an imperative style. And if you think back to my car example that I showed you before, where I highlighted functional composition, but that's all well and good, but what happens if we need to add some error handling, or if we need to add some asynchronous tasks within there? So functional programming allows us to do that by taking values such as a car instance or a string and placing it inside a container. And then what we can do is we can abstract over those values and just deal at the container level. And we can still perform these special operations like error handling whilst still being able to chain these functions together and still allowing the code to flow through. So in Scala, try is one of those containers. So what we're doing here, we're wrapping some code that may or may not throw an exception, and the try container will catch it if it does throw an exception. So here we're trying to convert a string into an integer, and all we're doing is just wrapping it inside our try. And what we get out of it is a try of type int. So what that'll actually give us is either if it's successful, so in other words, if there's no exception thrown, then we'll get a successful try with inside it an integer. If it does throw an exception, then we'll get a failed try with our exception inside. But the key is here that there isn't an exception thrown that's just going to completely bomb out of our code. So once we've got this, what happens if we want to check, want to do some manipulation of that value inside our try? So what happens if we wanted to check if it's even, say? So there's a function called .map, and we can call that on our containers. So here we can pass in the isEven function that we created earlier into our .map function. And what that's going to do is it's going to say if the try was successful, then I'm going to apply the function that we passed in on the value that's contained within the try. So what that's ultimately doing is converting it from a try of int to a try of Boolean, because our function takes in an int and returns a Boolean. So it's performing the operation inside the try. But it's only going to do that if the try was successful. So in other words, if it's a failed try, what it'll do is it just give us back a new instance of the try with the same exception contained within it. So as you can see here, the middle line and the bottom line are both the same. So we're not letting the throwing and catching of exceptions dictate our flow control. Instead, what we're doing is passing around our try container and performing operations on it based on the fact that it was successful. So another example, we've got a songs database here, and we're calling off to that, but we don't know how long it's going to take. It might take ages. So how do we run this asynchronously in a functional world? So Scala Future is another type of container, and this is one where we can execute code in an asynchronous fashion. So this is similar to JavaScript promises, if you've come across those. And this is how we create concurrent and parallel code in Scala. So again, all we're doing is we're wrapping our code that we're going to execute inside our future container. And then that will execute the code asynchronously. And what we can do is we can set up our code so that it will perform operations afterwards, assuming that that will have finished. So once the future is finished, which could be at any time, then we define the code that will carry on after that future is finished. So let's see what that might look like. So I've introduced another dependency here, which is the lyrics API. So lyrics API will take in a song type and give us back a string. So I'm combining these together conceptually. You take a song title, you pass it into the songs database, you get back your song, and then you pass that song into the API, and then that'll give you back the lyrics. So I haven't got time, unfortunately, to go through the syntax of this, but this is called a for comprehension in Scala. And what it's essentially doing is it's essentially linking the first call with the second call. So it's linking those two futures together. But the key is it's non-thread blocking. So in other words, we could, in theory, take the first future call, go off to our database, come back, and then perform a number of tasks in between, and then eventually call the lyrics API on the first future. So we're not blocking any of our code at that point. And again, to emphasize, we're abstracting over those container values. So the values inside are a string to a song to a string again, but we're just dealing with the high level future. So I hope you can see that this allows us to still sort of let our data flow through our system when we're checking and manipulating the values inside of these containers. But again, we've still got that flow. So containers are known as monads in the functional world. They're a little bit more advanced than what I've talked about so far, and they should really have their own dedicated presentation. But hopefully they're giving you a glimpse of how important they are in functional programming. So I spent a lot of time bigging up functional programming, so I might as well go through the downsides as well. So they are hard concepts to understand. It's based on mathematical theory, so it can be quite difficult to get your head around. And it's a lot easier to manipulate global state in an application than it is to come at it from a functional point of view. It can be used to create complex code. This was a taster of what functional programming can be, but it can get a lot more advanced. It start introducing category theory, so it can create heavy code, which therefore can rely on it, can cause it to be quite a steep learning curve for new starters. But as a team, you can decide on how advanced you become within the functional world. You can decide that where the boundaries and where the scope is of your functional knowledge of what you implement. Immutability and recursion, can increase RAM slightly, but as we know, memory is very cheap, and functional programming languages have very clever ways of managing memory. So it's not a big deal, but it is still a consideration. And then lastly, combining functions is hard. Creating one pure function is really easy, but actually chaining them together and chaining monads together becomes a little bit more tricky. So in reality, my team day to day, we don't mutate state, we don't throw exceptions, and we love monads, but we don't have that special silo area of code, that functional core I was talking about before. We do have classes that are dedicated to just doing I/O, so HTTP calls, database calls, but I think that's just clean code rather than following a functional sort of paradigm. And we also do log in most areas of the code. I think logging is quite difficult to negotiate when you're dealing with the definition of a pure function. But I don't think that this should render the entire paradigm redundant. I think I've shown you so many advantages to it, even if you consider that logging is impure. So this brings me to the controversy. So Java and JavaScript and Scala, because they can mutate state, you are able to mutate state. There are people in the FP community that don't consider them functional languages. They're considered as non-pure languages, whereas something like Haskell is considered a pure functional language. But I mean, your language might not have the advanced features of monads, but as I say, most languages will support first-class functions and higher-order functions. And it's just a sliding scale, really, of how much your language will give you in terms of helping you down the functional programming route. And finally, as far as the controversy goes, I think FP is a simple guide, in which we can help write better code. We shouldn't be going to war over it. They aren't laws that people can break ultimately. And then lastly, so this is a great book that is fantastic. It's written using Scala examples similar to what I have done, but the content is the main thing. The level in which it comes at it explains it in a really understandable way. Some books can be very, very dense and very hard to understand when looking at functional programming. And there is a free PDF that gives you about 50% of the content, so I'd definitely check that out. For those at the BBC, there is a Slack channel, functional programming. It's gone quiet the last sort of 6 months or so, maybe even longer. So hopefully talks like this will kickstart it again. And then there's some exercises there. You're thinking of taking up Scala, I'd definitely recommend it. And there's also a really good Medium article that you can Google when going from OOP to functional programming.